welcome all, and thanks to Science and Cocktails for asking me to come in tonight and give a little bit of a talk about our facility and what goes on at it, and what we're working on, and where we expect to go with it, and what I think you can hear from us in the coming few months and years from the Atacama Large Millimeter Submillimeter Array. So throughout the course of the next roughly hour, if you're still awake with me by the end, I'm going to start off covering a little bit about what the millimeter, submillimeter aspects of this mean. So what is submillimeter science? What kind of things can you study, basically, in general? And then we'll move on to the definition of really what the array is and what that means from the point of view of the kind of things we can study. And then I'll talk a bit about the Atacama portion, including some of the fun social interactions that we have given where the telescope is. And then finally, if there's time left, I'll actually talk about the science. Hopefully I'll spend at least half of the time on that and not quite so much on the beginning. So here, this little cartoon here is really just trying to highlight what exactly we can study with submillimeter astronomy. So obviously, submillimeter is anything smaller than a millimeter, but from the point of view of astronomy, it's really the farthest of the far infrared aspects of the spectrum. So it's anything from 7 millimeter wavelength is kind of the limit of what we look at, to about 250 microns, or a quarter of a millimeter. So basically from a little bit less than the width of your pinky down to about the width of 10 human hairs. That's the wavelength of light that we're looking at. But that really just translates into colors of heat that we have at the that we're able to see with the telescope. Now, of course, the sun itself is a little over 5,000 degrees, and it peaks out in the yellow, obviously, since it's a bit on the yellowish side. And in the infrared, us as warm bodies at 37 Celsius are emitting in the sort of nearish infrared side. If you go down to kind of on the order of, say, minus 150 or down to minus 260 degrees Celsius, near sort of 10 degrees above absolute zero, you're peaking out in the far infrared. And that's why we built ALMA, because we wanted to study the coldest material that we have in the universe. And why do you want to do that, of course, is because most of the material out of which interesting things eventually form in the universe starts out as really cold material. And so we end up studying things roughly in this temperature range, by and large. There are some things that we study that are sort of outside of that are driven by processes that aren't basically heat. But what we're looking at is bodies that are between 10 degrees above absolute zero up to about 150 degrees above absolute zero. And that's really what the array was designed to study. So what kind of stuff in the universe is at that temperature? Well, it's gas and dust. Now, before all of you get up and leave because you're thinking, God, I came here tonight and I'm going to hear about gas and dust, let's think about it here for a minute. I mean, a big rock, what is a big rock really? Well, a big rock is actually just a bunch of compressed dust at the end of the day. And gas is basically everything we're walking around in. So if you want to understand, at least my biggest motivation in all of this, is how we got this, how we came to be standing on a rock here that has enough air that we can breathe and run around and do all of the exciting things that we can do. That comes out of gas and dust. So if you want to form the Earth, you need to understand what's going on with the gas and dust in the universe. So here is an image, sort of artist conception level of a nearby, this is an A star. This is supposed to look like the Fomalhaut image from long ago. But basically, what that is dust. It's dust grains. So that dust grain was a few microns in size, so a pretty tiny one. But what we study at the array is slightly bigger dust grains. And those dust grains are the things that actually represent the bulk of the solid material that there is in space that goes into forming planets and stars and subsequently galaxies in a sort of a completely different scale. So dust is actually interesting, and we spent €1 billion to build a facility to study it. The other thing is that we can study is actually gas. So I know that there are some in the audience that can probably calculate what I'm going to talk about from first principles quantum mechanically, but just bear with me for a few moments. The other thing we can study is molecules. So back in the 50s, we didn't really think that you can actually make molecules in space. We thought that they would be destroyed quickly and readily in their sort of high UV X-ray environments. But it turns out that they're pretty prevalent. And if you want to find a molecule it has to be excited and it has to de-excite. So like your atomic transitions that we all studied in high school, molecules kind of act the same way. So you can excite a molecule electrically, and its electrons can do exciting things, and then they decay back to their ground state and they emit light. But that only happens at relatively high temperatures. So for the point of view of ALMA, we really don't care about that so much. So what else can molecules do? Well, molecules can vibrate and they can rotate. So you can have two molecules and they can do exciting things like this, and they can do that again. And they can keep doing this indefinitely. And then they can actually change and they can do it more slowly. And they keep doing it. But given the quantum mechanical nature of molecules, they can only do that at very specific states. So that molecule can only vibrate in and out at specific frequencies. And when it transitions, it can only vibrate at a specific lower frequency. And so that's why when you get this ray of light emitted, it gets emitted at a very specific point in frequency. So this axis is roughly arbitrary units. It's actually terahertz for those who are interested in the audience. It emits at a pretty specific frequency. It can be a little bit, the color can be a little bit different if you imagine this is not a frequency but as a color of light. It can be a little bit bluer, a little bit redder if the molecule happens to be moving away from you or towards you, but for the most part it's confined to a really narrow range. Now if it went to an even lower state from this state, it would emit a slightly higher wavelength of light, slightly higher, slightly redder, bluer color, let's call it. But it would do so, again, at a very specific frequency. So we're getting somewhere, trust me. All right, the other things I said the molecules can do is they can spin. But again, given their quantum mechanical nature, they can only spin at specific rates. So we have this guy here, he spins around. Why this is carbon monoxide will become clear later. But so this thing can spin around, and it's very nice, and it can also vibrate at the same time. But if it's just spinning, it can also spin, again, more slowly. But again, at a specific frequency. So it emits a very narrow color spectrum of light. And if it was spinning even more slowly than that from this excited state, it would emit something at slightly higher frequency. So again, slightly bluer color. But again, at a specific frequency. So this is all great. It's easy. So basically what we've done here is we figured out that we can actually thumbprint carbon monoxide. So if we have something that contains carbon monoxide, and we know roughly how fast the thing is going overall, or we can actually determine how fast it's going, you'll see a very specific spectrum, and that tells you carbon monoxide is here. And that's great, and you can actually, like I said, some of you can probably even do it. I did it a long time ago. I couldn't do it today. You can actually calculate this from first principles and actually derive what these frequencies should be. Now, that's great, but of course, space is a little more complicated than that. So we have here spinning molecules. It's actually a lot of what we've got in the back. This is ethanol. Now, if you take a thumbprint of ethanol, it's a volatile, so it's a little bit less tightly bound, and so it can vibrate and spin at the same time. This is the thumbprint of ethanol in a very restricted range of frequencies. So instead of one line, which when we looked at carbon monoxide, we would have had a single line roughly right here, very bright, and everything else would have been out of the picture. But with ethanol, we have hundreds of lines. So we can actually, again, thumbprint ethanol spectrally if we can see it in the universe. All right. So moving away from the sort of generic picture now, gas and dust, we can figure out how what the temperature is based on where it peaks in its spectrum of how warm the dust is. It shifts its peak around. And we can also thumbprint specific molecules by matching up with their spectra, the colors that they emit at these specific wavelengths. All right, so that's, in a nutshell, the kind of things that we can do with the array. Now, what is the array in general? Well, the array is actually a collection of relatively small telescopes. Let's call them radio telescopes that are 12 meters in diameter. And we have 66 of them. But what we try to do is effectively simulate or synthesize, in reality, a telescope that is actually the size of the maximum separation of the antennas. So we have antenna here, and we have antennas over here, and so what I hope to convince you of is that we can actually synthesize something based on the image that we can create from these two telescopes, at least something that looks like that resolution. So with the telescope, of course, the bigger the telescope is, the higher the resolution you should be able to have on the sky. Now, what actually matters here is not the individual telescopes themselves, it's actually the pairs of telescopes. So what we're doing here is we're sampling the size of this telescope pairwise. So we recover this portion of the telescope aperture, the plane of the telescope, with this pair, and then with this pair we cover a different size scale. And with these in the middle, we capture very small size scales. And in the end, we can actually capture all of the combined size scales by allowing the Earth to help us. So while the Earth is rotating underneath the object, these antennas effectively move within this aperture, and they also get closer to each other. Now, what do I mean by that? So we have a friend, our dark cloud, which is made up of gas and dust, right? It's up here. And when these two antennas are looking at it when it's over here, their separation looks like this, roughly. Now, as the Earth spins, and say 5 hours later, the dark cloud of gas and dust is here. And it's looking down in this direction, but its projection, according to what the source effectively would see if it was looking at the antennas, is a shorter baseline. This is just like if you have an object in the distance that tilts away from you, it starts to look shorter, right? I mean, it's effectively the same situation. So as the Earth is rotating under this, these antennas they're moving within the plane, and they're also getting closer together. So we can start to sample the full of this aperture. Now, for those who want to go look up and do things at home, you're actually taking a Fourier sample of the telescope aperture plane, that when you do a transform of that, you actually recover the image plane. But that's for those who want to do homework later. So what happens after we detect the signal? So we have the signal coming into the antenna, and it comes in as basically a vibration within the current that we have running through a little detector in here. Now that detector is operating at a temperature of 4 degrees above absolute zero. So we have to have very supercooled cryogenic systems, because the only way you can detect the light coming in, it's so weak, is with a superconductor. So we have a bunch of superconducting devices that are sitting back here, and they're all cooled with liquid helium down to 4 degrees above absolute zero. Now, the amount of energy that we're trying to detect is effectively the same as a melting snowflake. So that's why we have to have hypercooled superconducting detectors to be able to see this, because the energy basically sends the superconductor from one state to another, and we can tell whether or not something is happening or not. So the signal comes out the back end of the telescope. We then digitize it, turn it into a series of ones and zeros instead of this nice analog oscillating signal. And then we also take the signals from the other antennas and we correlate them with each other. So we have a giant supercomputer. It's the highest supercomputer on the face of the Earth. And it does all of the correlations between all sort of roughly 2,000 pairs of antennas that we have on site. And then it sends the signal, which is both taken in terms of measuring the intensity, but it also measures the color distribution of the light coming in by lagging the signal. So you can actually delay one signal reference to the other, and that actually creates a color spectrum of what's coming out the back end of the telescope. Now, what does this mean for actually taking images and what you can do with it? So here we have 3 source models on the left. We have a point, very boring. We use these sorts of things as calibration sources all the time because they have a very clean signal. And then you have 4 little sources that are of different brightnesses. And then you have a thermal image of Albert Einstein's head. So in the first 2 columns, you have 16 antennas. So you can create pairs between all of those 16 antennas. And we observe it for 10 minutes or 4 hours. So this is allowing the Earth rotation to do something for you. And now you can see that no matter how many antennas we have or however long we observe it, when we have a nice simple image, you see it in both senses. But when things get a little bit more complicated, you do quite well on the bright and obvious things, but this guy only shows up after you've allowed the Earth to help you by rotating underneath of you for 4 hours. And Albert Einstein is nowhere present, frankly. So here is the sample of pairs that we can make of the antennas. So each point on there is basically 2 antennas at a given distance. So here, here, all over the place. And this is what happens when you let the Earth take that pattern and rotate for 4 hours and recover a variety of samples. So if you wanted to create the perfect telescope, the size of the maximum separation of antennas, you would need this to be solid blue. Then you would effectively have recovered exactly the image of what a telescope of that size would be. Now, if you've got 50 antennas, which is what I operate with most of the time, and you have the 10 minutes, not only do you get the point and you get all 4 sources, but you actually get an image that starts to look like Albert Einstein. And that's because you have so many more pairs that compared to this, you filled in practically everything, right? And if you let it rotate even for just 1 hour, you fill in almost all of the little spaces, except for that darn one in the middle that's a little bit more complicated to deal with. And you actually start to recover something that actually really looks like Albert Einstein. So this is effectively what the telescope is looking at. This is, say, a dust point, a very small dust source on the sky, or a very, very distant galaxy. And we observe it with the antennas spread over several hours, and we can actually recover not just simple structure, but we can actually recover very complicated looking structures. So we can make very high quality images on the sky with an array of 50 antennas in about an hour. So this will become important when we get to the actual images of real things. But now I'll move on to what it means to be Atacama and large. So first, a little bit on the sociology of the project. What is the Atacama Large Telescope in terms of its function and creation? So this is a map of the world. The project is actually a collaboration of 3 institutes around the world. So the National Institute of Natural Sciences in Japan, the National Science Foundation in cooperation with the National Research Council in Canada, US plus Canada, and then the European Southern Observatory from the European side. This is 25% of the project, and these two have split the rest 37.5% even. What happened basically is all 3 of these institutes wanted to build their own telescope, but they couldn't build one big enough on their own. So they pooled their money, came up with basically in 2006 currency, 1 billion euros to create the telescope in Chile. Now, why in Chile, we'll get to throughout the course of explaining why Atacama and large. But just to give you an idea of what happens here within the European segment, the headquarters is near Munich in Garching. There's a Max Planck Institute there as well. But there are also little hubs of support around the rest of Europe. So if you happen to live near any one of these centers, Lisbon, Grenoble, Bologna, Bonn / Cologne, Leiden, Manchester, or Gothenburg, you can actually go and you can learn how to use the telescope, and they will help you process your data and get your Nobel Prize moment out of ALMA. But that's very specific for the European model of things. In the US, there's 1 center in Charlottesville, Virginia, and in Japan, the main center is in Tokyo, where I was at before I came here last week. All right, so a little bit more about why we're in the Atacama. Well, the first thing to understand is that the enemy of submillimeter astronomy is water. We like to detect water, that's a different story. But water does really evil things to the signal, submillimeter signal coming from space. So this is, although it says the plane of Shad-Natura, this is actually a model of what the conditions would produce in Onsala Space Observatory, which is in Gothenburg. So at a typical amount of water, so they're equivalent to 15 millimeters of pool above you, integrating over the whole atmosphere. The submillimeter band starts kind of, let's call it here, and the red line represents what gets through from the top of the atmosphere. So if you put a source outside the atmosphere and you tried to observe it at submillimeter wavelengths from Onsala, you'd be lucky to get 20% of the signal out, and in reality, you'd get nothing in most of the bands. Now, most of the dust we're interested in observing, and some of the most interesting molecules, actually peak their emission in the purple band, the brown band, the green band, and the teal band. So that's not a really good place to be if you want to observe cold gas and dust in the universe. So I came, before working for ALMA, from the Combined Array for Research in Millimeter Astronomy, which is a Caltech and University of California collaboration in Central California. So this is at 2,000 meters, not at sea level. So you're starting to get above the water simply by moving the telescope up in the air. And also in the Mojave Desert. And here you're starting to see, 40% of the signal gets through the atmosphere and some of the places that I want to see, but it's not fantastic. And down here, we're lucky to see 5%. Now, if we go to the driest desert on the face of the Earth at 5,000 meters altitude, which is where ALMA is located, you get the red and the green. The red is a sort of okay day on the ALMA plateau. And here you're starting to see 20% of the most difficult window comes through. So the dust that you really want to observe in this window, because it's where it peaks its emission, so you get the most brightness out of your source, so you can study it to the best extent possible. But actually on a really good day at ALMA, you've got 1/4 of a millimeter of water above your head, and you actually can see 80% of the signal coming through. So this is why we want to get high and we want to get dry, and that's why we're in northern Chile. So to just give you an idea of exactly where we are, if you start in Santiago, you get on a plane, and you fly for a couple of hours to a beautiful mining town called Calama, which is a jewel, let me tell you. You then get on a bus, and you travel to the tourist center of San Pedro de Atacama, which I expect that some in the audience have actually been to. There's a lot of really cool desert scenery and sort of salt mountains, which are really beautifully sculpted by the water and, by the wind. And then you can get on a Jeep from San Pedro de Atacama and go for about 45 minutes, and you get to the ALMA site. So what does the ALMA site look like? We've got 2 sites, basically. The support facility, which is where we live, basically. It's a village of about 200 people that has 2 populations. It's got one population one week and another population the other week. We're isolated enough in San Pedro, even if you've been there for tourist purposes, it's not a great place to live. So we actually have an entire village of astronomers and engineers, effectively, that live on site. This is the antennas where we maintain them down this is at 3,000 meters elevation. That's where we live, dormitory buildings and whatnot. That's a volcano called Lincon, which has got mines all over the back half of it from a war not quite a while ago. But in general, you see the full of the nations of the project are represented by the flagpoles. The control room for the telescope is actually located at this altitude. And that's frankly because nobody wants to be at 5,000 meters doing anything if they can avoid it. It's unpleasant and you get stupid very quickly. I once tried to do some things up at that altitude, and I was observing with my partner, and she kept asking me to sort of give the next scan number of that we were on so that we could record it in the log. And after about, as we'd been up there for most of the night, she asked me for a number, and I was like, okay, the next one is 2,347, and she's like, the last one was 2,347. So I'm like, oh, that's strange. So I look at the sheet, and actually the previous 14 had been 2,347. So we had to go back and edit the logs because, like I said, you get stupid up at the high altitude. So you want to spend as much of your time down here, and it's actually not a random occurrence that we're here. Chilean regulation about working at altitude changes really dramatically at 3,000 meters. So the camp facility is located at 2,995 meters. Okay, we are not the only inhabitants of the area. There is some wildlife hanging around, and there are also a local population. The area around San Pedro has been inhabited for about 12,000 years. And there is still a strong and vibrant local community, indigenous community in the area, and we try to work with them as best we can. So we support the local schools by providing science education for the Lincoln and Thai people. We also actually have to get permission for doing a variety of things that we do. So we have a back road that we use that passes through one farm. It's technically a farm, but they don't grow a lot of things because it just doesn't grow. Pass through a gate on their land periodically. And we also involve the local priest and priestesses anytime we start doing any new activity on site. We dedicate it with a ceremony called Pachamama, which does involve wine. It's actually one of the few times that we allow alcohol on site, because if you want to get really stupid, don't just go to 5,000 meters, drink there. and then you really can't stand up at all. So now moving up to the 5,000 meter site and seeing a little bit more about what's going on at the array. So this is giving you a drone flyover. And in fact, the creation of this video was really difficult in general because drones don't fly that well at 5,000 meters altitude. But this was a fairly heavy-duty item that was able to lift the payload of the camera and get us some footage. So basically, the surface of the array, we want to be high, we want to be dry, so we're up at 5,000 meters, and we also want to we want to have the antennas as far apart as possible, so we need flat in a big area. And this is really the only place on Earth that provides that. So we do get some snow, and you actually see some very interesting sculpture within the snow, and eventually we'll do a flyover close to the snow, and you'll see a differential sublimation of the snow. It creates these kind of spires. It's a pretty interesting feature being up there in the wintertime. But bottom line, it looks like the surface of Mars for the most part. If you've seen the videos from the Mars rovers, you don't see much that looks very different up here. It's a very harsh environment in terms of the UV radiation. We're baking these telescopes, but they also have to be super accurate down to the sort of less than half a human hair, the surface accuracy of these dishes, in order otherwise they don't function. So it's a pretty harsh environment. Again, you don't want to be working up here as much as possible, but of course daily I send about 30 people up to the high site working with oxygen the entire time to be able to actually perform the regular maintenance on the array that they have to do in order to keep it working very well. And also off to the side, you saw once or twice maybe there's a building, and inside that building is an atomic clock and a supercomputer. And that basically, those are responsible for sending out the heartbeat to the array so that we can align all the signals when they come back in. And the supercomputer is responsible for combining those signals when they come back. Now, the other thing that we have to do with the telescopes in order to really fill that plane, right, to make those blue dots fill the entire plane, is we have to actually move the telescopes. They don't move enough simply by having the Earth rotate under them. So we have to actually pick them up and physically move them. They weigh about 130 tons each, and we have to set them down to an accuracy of about 1 millimeter. So we have a special machine that does that. And on the right side, each one of these white dots is actually an antenna. So every time they're down here at our base camp, they come up to the array. And this image covers the entire set of movements that was made between 2009 and 2014. 2014 was the first time that we occupied these most extended positions on the map. This is not a linear plot. These are actually really far away. So this is sort of 15 kilometers from here to here. And within this, it's sort of more like 500 meters. So it's not exactly a linear plot of the distances. But here you see we start to move the antennas a little bit farther out. And here we needed to take this one down to do maintenance on it, so it's one of the dots that's going back down. And then we bring another one in because we really wanted to have these two antennas super close to each other, because there are certain types of calibrations that you only can do when the antennas are really close to each other. So we actually just picked one up, moved it down, and put another one down in its place. And that took, I mean, this is time-lapse video, took about pretty much the entire daylight time to pick one up, set it down, and move the other one. So you can imagine the amount of effort that goes into moving all of the antennas that we saw on this right side. And it's really set just so that we can fill that plane, so we can make the most complete images as possible. And you'll see now why making those images, superfine images, is really important. So, all right, now we're actually going to get on to the science portion of things. So I'm going to cover 3 major areas that are sort of core to what ALMA does, and that is chemistry. So we're trying to look for the origins of life, effectively. So we're trying to thumbprint a molecule that is actually one of the bases for biological life. Now, it's complicated, and we'll get there. The other thing that we look at is how planets form. So how do you actually get this thing that we're sitting on tonight, or standing on, or walking around pacing? How did we actually form it? How did it get here out of a cloud of gas and dust, right? So how do we end up with this giant rock that is able to support life out of a bunch of fluffy gas and dust? And the other thing we look at is the bulk of material in the early universe. So how do you get a galaxy together, or how many galaxies got together at a given time that could form stars early on in the universe? Because forming that first population of stars is really important, because the earliest stars, they just burn hydrogen and helium and then they blow. But in order to do much better than that, you have to be burning carbon and nitrogen and oxygen in the special process that allows stars to burn fuel longer. But if you don't have carbon, nitrogen, and oxygen, you need to create it. And you can only do that after you've had one round of stars form and then explode. So we really want to understand how we got that material together in the earliest galaxies. So we'll go through the three topics here really quickly. And the first one is chemistry and the origins of life. So we talked about this guy. This is a favorite because it has a very strong signal. It's a very imbalanced molecule, effectively, in a quantum mechanical sense. And so it has a really strong emission. You don't need very much material to actually see it. Now, most of the molecular matter in the universe is this, because most of the matter in the universe is hydrogen. But this is actually really hard to see for reasons that I won't get into. But effectively, it's so balanced because it's just the same thing. You actually don't see any emission from it kind of at the first level. You have to go to sort of secondary effects before you see it. Now, sort of we have a suite of basic molecules. We have cyanide, which is a lot of the stuff in space is not very pleasant. Sulfur monoxide, methane. Water there too, also ammonia. So there's a lot of toxic stuff. Now we can get a little bit more complicated. We can get some more toxic stuff like formaldehyde or nitrous oxide. Salt or potassium chloride, if you've got high blood pressure, you can get that instead. But in general, we have a variety of intermediate complexity molecules floating around out there too. Now, we can also get really complicated. So we can get into methanol, methyl cyanide, and a variety of other sort of fairly complicated molecules. Or we can go nuts and see things like, here's ethanol from before, dimethyl ether, methylformate. So there's a lot of really complicated stuff out there too. And remember that thumbprint, right? So if you just had these guys floating around out there, it wouldn't be that big a deal. It wouldn't be that complicated. But now you can imagine, given that I showed you just the light spectrum of this, so the thumbprint of ethanol, and you've got all these other things, and of course the more bonds you have between molecules, the more complicated your thumbprint gets. So you actually end up with something that looks like this. And in fact, there are over 200 chemical species that have been detected in space. And not all of them are nice, simple, easy things to look at. So what does it look like with ALMA when we try to figure out and try to find some of these origins of life? Well, it looks like this. This is actually data from an early paper by Jes Jorgensen, who has a group here in Copenhagen, actually, that does this sort of looking for the signs of biological life. So what do you do with this mess of things? Well, you basically have your toolkit. You have your set of thumbprints from all of these different molecules that you know, either because you've detected them and you've calculated their spectrum from quantum mechanics, or if you have to, you have some other method of getting a hold of them. And you start to fit them. So the first thing he does is he puts in methanol, which is the red. I'm going to lock that in. Now let's find a derivative of methanol. We lock that in. Then we get some methylformate with the red, and so we lock that in, and we start to add these up to get the yellow portions of the spectrum, trying to match the blue spectrum, sort of empirically going through. Now, then he adds a whole lot of other sort of low-level, fairly faint species, and he tries to build up a picture of exactly what this looks like. And of course, do you think he's going to match it perfectly? No. So what do we do then? Well, we take a step back, and we try to focus on an area where we didn't match perfectly. So there's actually a fairly significant set of blue here that isn't perfectly matched up. So we zoom in on that, and then we try to figure out what these molecules are by matching other things. Now, you can only get so far with this before you can't really calculate or know things particularly easily. So what's been happening in the last 3 or 4 years is that we have the residuals of this from ALMA. Like, this is a really booming line at some level that's left over that's got no partner. We collaborated with laboratory chemists. So basically, you recreate the conditions of space in a chamber in a laboratory, and you inject something in there that you know what it is, and then you look at what its thumbprint is. So you build up your toolkit empirically in this way. And so as for now, starting with the complicated spectrum that we had at the beginning, about 30% of that, we don't know what it is. So we've got to get there if we want to actually figure out how and where prebiotic molecules are sitting in space and how they can evolve by looking at different regions. But two things that have really come out a few years ago that were sort of pathfinders in this area. And one is the finding of glycolaldehyde, which is a simple sugar, and effectively can be seen as a precursor to sort of an amino acid or more complex sugars that might be of interest to a biological form that wanted to get together. And in a similar way, with a different telescope, a giant single-dish telescope, we've actually detected chirality in molecules. So this is the handedness of a molecule. So we've actually found that in the universe, in a variety of ways, handedness becomes a big deal. So you end up converging towards one hand versus the other. This is how we have matter instead of antimatter. At some point in the past, the universe developed a taste for one thing rather than another, and it actually becomes rather important for biological processes as well, this chirality. So you see a molecule where whether or not this molecule is on that side, or if you flipped it over, you would have to switch the side of that molecule. It would come out of the page rather than in the page. And so that was detected near the galactic center, so that's sort of a violent place to be. But this was actually detected in a system that you can imagine was a precursor to the solar system. So this is its phone number is IRAS 16293. Again, if you want to look it up at home later. But basically, we've discovered a simple sugar here, and we did that basically by taking laboratory data and matching it with space. Now, more recently in the laboratory, we've managed to effectively synthesize ribose, which is one of the principal things in RNA. So we're getting there. We were able to make an element of RNA in the laboratory in space-like conditions and get its thumbprint. So now we need to go back to this and see if we can match up any of the peaks in this spectrum to the thumbprint of ribose or some other similar molecule. So this is an active area of research going on day to day. But there's something that we're doing at the array to make this better. So we're actually expanding the space over which we can cover the thumbprints by about a factor of 8 over the next few years. And so that should allow these studies to go much more quickly. So you can actually cover a lot of space for lines in a short amount of time. And hopefully this will help us develop towards really seeing these sort of precursors of life. And I expect that 200 plus number to become 500 plus in probably the next couple of years, and then we'll get into the multiple thousands by the middle of the next decade as we expand the capability of the system. All right, now we get into what I got into the business for. So this is how do we form planets, basically. How do we actually get here? And we start with gas and dust, right? So we have a big blob of gas and dust that's sitting in the galaxy. It's just sort of a knot out there. But the galaxy's rotating, and so at some level, this guy is rotating a little bit too. There's also some things that might locally excite rotation. And it spins a little bit, and let's say it gets really dense at the middle, and so it starts to attract itself under gravity. So it collapses. But remembering back again to our high school physics, if you've got something spinning, things can fall along the axis of rotation relatively easily. So at the middle, you're going to form a star, probably, as this continues to compact. And the material here falls directly in, and this material can fall fairly straight in as well. But the material here can't fall in because it's rotating. Conservation of angular momentum. So instead, at the end, what you get is a star, a forming star at the middle, and a flat disk of material orbiting around it. Now, this is a post-ALMA 2014 image, so it looks nice and structured, and there's a lot of very interesting stuff going on in there. And then eventually, you hit planets orbiting around a nice star that looks oddly like the sun. And this is the sort of basic cartoonal process of forming a planet. Now, of course, the hard question is what happens between here and here. So this onset is pretty straightforward. We kind of understand how that's going. And we can get to this, but the problem is that up until the advent of ALMA, all of these looked like nice, flat, smooth, regularly shaped things. So what we saw was something more like, if we look in from now edge on, was something like this, where you have sort of dusty grains in the middle, and you've got dusty grains out here that have actually formed some ice crystals on top of them. But if you were to look at this from above, you would basically see a nice smooth progression along this direction. That was really a problem. So you can imagine if you've got pebbles, sort of small rocks, a couple centimeter size in a disk, and they're rotating around, and they're kind of moving randomly a little bit with respect to each other, and they slam into each other. What are they going to do? Well, generally speaking, they shatter each other, right? But if we want to get from a rock that size to the size of a mountain, well, they can't shatter. They have to actually coagulate and stick together. Now, that's really hard to do physically in a flat disk with no structure, no sort of general process of anything going on, just a nice, smoothly rotating disk. But if you can get some substructure in there, you can actually start to do some things, because the particles get closer together, and the denser regions, they generally move slower with respect to each other, so the probability of them sticking together goes up. So fast forward to ALMA, you'll note that none of these look flat and smooth at all. This was the first one that we looked at. So this is, the HL here basically means it's a variable star. The Taurus means it's in the constellation of Taurus. So this object has been known for practically more than a century. Not quite, but getting close to it. And this was actually the first object that was looked at after a satellite was launched in the mid-'80s. And basically, this was the thing that allowed us to discover that things were in a disk, because they saw the central star, and they saw all this stuff left over, and they basically did a quick calculation that showed that if it was a spherical distribution around the central star, you wouldn't see the star. It would have been blocked by the dust around the star. But you saw the star, which meant that it had to be flattened in some way. But all of the higher resolution imaging that we had done with other facilities since then showed a nice, smooth, regular thing. So again, supporting this problem of getting from the pebble size to the mountain size. And once you get a mountain, you have gravity, and you can attract other mountains, and then you stick together from that. But if you're small enough, you don't really have enough gravity to stick together. So we decided that we were going to look at this at the first time we ever moved the antennas far apart from each other. And what we were likely to see was nothing. The way the telescope functions, it sees differences extraordinarily well. But if you have something flat and smooth, it actually doesn't detect it very, very much. So we were either going to see nothing, or we were going to see a mess. That was our prediction. So this is a very young object, sort of 100,000 years old or so. And when you're that young, you're in this phase, and you've got all these like vortices and things flowing around, and there are streams coming in from here, and a lot of spinning of things that haven't really settled down. So we thought we were either going to see a mess, or we were going to see nothing because it was going to be perfectly flat. And in the end, I ended up crying in the Lego store at a mall in Santiago, because I got an image of this with a statement that this is not a model, from one of the visitors that we had down helping us with the imaging process here. So this actually then ended up creating a different problem. So instead of having a mess or something flat and not knowing how to form something big, we get to the opposite problem, that we already have big stuff. So how did it get there? So the easiest ways to make nice, even rings like this is to have a young planet sitting in that ring, clearing out the material as it orbits around the central star. So we had gone from having a problem of, I can't form a planet fast enough, to, oh my God, I have too many planets too early, and I don't know what to do with them all. Now, the good thing is, once you get one planet, you can actually create these rings through resonances and other things, but you've got to at least get one in there, really, in order to start the process going. And that was sort of our general finding with this. Now we've got another, this is TW Hydra, this is a little bit closer than HL Tau, not quite as massive. This looks like it's forming a multiple system. This looks kind of like these. This has got some nice spiral arms. This has got a really bright ring with a huge gap, and then a fainter ring around the outside. But bottom line is we have a lot more structure here, and it's happening far earlier than we expected. So now we had to go back to the drawing board and really start talking about how do you form these massive particles that can clear out these gaps, sort of massive planetoid type things, sooner and earlier. And that's sort of the same thing that we've gotten from the chemistry studies. It almost really led us to needing to understand how we got more quickly rather than how we got it there at all. So it's really sort of flipped the textbook at this point, and we're really struggling to figure out how to form the sort of things that would get to this point that fast. But in terms of getting from there to an actual planet, at some level, that's easy now because they're already there at early phases. We've just got to figure out how they form as early as they seem to. All right, so we'll move on to the third category now of, this is on the galaxy side. So we have, so in the distant universe, galaxies are made up of gas and dust, and that gas is cold, and it has the thumbprint. And the good thing about galaxies at large enough distances is due to the expansion of the universe, the farther away they are, the more shifted their line gets. So if you can actually figure out how to thumbprint the gas effectively, you can actually figure out how far away and or how old the object is. So what we've done here is this is done with the original ALMA with 16 antennas. Now the cool thing here is that doing one of these sources on a precursor telescope to ALMA would take you a couple of days to observe. So you'd pound on this thing with the best telescope available for ALMA for a few days, and you would get something that looked pretty much this good. Maybe not quite that good, but pretty much. So when ALMA came up, well, you can imagine that if you want to study what a galaxy over there is doing, and then get a distance to another galaxy, and get another distance to another galaxy, so you can actually do a statistical analysis of how much gas is where at a given time, because that's really the goal here, is to figure out, you know, as a function of distance, what the gas is effectively doing. How much of it is it there? I mean, how bright is the line? How hot is it, which determines how wide the line is. And then, of course, you need to know where it is by the redshift. So you can see these lines are basically all CO lines for the most part. Again, carbon monoxide is our friend in space. And you can thumbprint, especially some of these like this one, you can actually get multiple lines. So you really nail this, the redshift of this one down at about 5, simply because you know that this can't be anything other than CO because it's too bright. And the fact that it's spaced at the right interval basically tells you it has to be CO. And then, of course, how much it's redshifted tells you really how far away it is. But you really need a statistical sample. So if you have to take days to do one of these, and of course there are other kinds of astronomers than people doing this, you don't really get much of a sample. Whereas if this whole thing was done in about 2 days of observing time. So we went from doing one in several days to doing many in 1 day, and that was with 16 antennas. And we've since really upped our game on this to with the 50 antennas. So we now have a huge sample of these that are really starting to take a look at what the gas reservoirs are doing and when you actually have sort of massive molecules in the early universe is something that we're really, we've been changing the game on that. And there's sort of a almost cottage industry at this point of measuring these redshifts. There's a new one coming out every day that I found the biggest, most distant reservoir of molecular gas. But it's really doing these things in ensemble and taking a look at what the distribution is that tells us about the density distribution in the early universe. And the other thing we can do is we can actually match all of these up and put them in the same frame of reference, pretending that they're galaxies all at the same distance, and stack them on top of each other and add them up. So what you can do with this is now you see our good friends, the CO lines. This is basically the 6 to 5 is just telling you it's changing from one rotation speed to another. And you see these lines are very bright, CO, 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 CO. But you also start to see some other interesting things. You start to see HCO+, you see hydrogen cyanide, You see water peaking up here. And effectively, you're starting to discover that we actually have a fairly complicated molecular universe, even at 1 billion years after the Big Bang. So again, ALMA telling us that things are more complicated earlier than we thought on the molecular level within the universe. And this is going on to this day. This was a result, sort of a game-changing result from about 2 years ago. But now, again, we're getting more and more of these. We're actually getting to the point where we can study the distribution of gas in these galaxies so far away and actually determine that they're polluting their environment with these heavy metals, even at slightly less than 1 billion years after the Big Bang. So the universe was doing a lot of interesting and exciting things very early in its youth, as is probably not all that different from people, I guess. All right, the final interesting point on the science side here is what you can do if you cheat a little bit. So if you happen to have a galaxy, a bunch of galaxies, a cluster of galaxies here, and it happens to have another galaxy much farther away but behind it, by general relativity, you can actually magnify this object because as the light goes out, it's bent by this cluster in front of it. And by pleasant geometry, if this happens to come together at about the distance of the Earth, you effectively get a lens. This acts as a lens, bending the light much like a lens refracts the light. And you can get to magnification of the source in the back, both in terms of its brightness and in terms of its spatial scale. So you can learn quite a bit about the brightness, and you learn a lot about the spatial scale. And you may ask yourself, how often does this really happen? The universe is really big. Well, it turns out, much like H.L. Tau, the first thing that we looked at when we moved the telescopes really far apart was SDP-81, which is a known source of this nature. And it looks like this. It's kind of Eye of Sauron looking at some level. So here the blue is a galaxy cluster taken with the Hubble Space Telescope. And the red, based on its carbon monoxide emission, our good friend, we can determine is actually very much farther away than the blue galaxy in front of it. And the good thing about this is that the form of the lens in front is fairly simple. It's a fairly smooth geometry. And the alignment isn't nearly perfect. In fact, even if the alignment was perfect, it wouldn't look like an exact full ring. This is about a perfect alignment as you can get. So the reality of the image at this distance is that it has a resolution of about 1,000 light years, right? Which is pretty good for something that's located at a tiny fraction of the age of the universe, back at a sort of 1.5 billion years after the Big Bang. But with the lens, you can actually reconstruct, so you can go backwards. If you know what the shape of the lens is and what its mass distribution is, you can actually regenerate the source as it looks if it hadn't been distorted. So this is a model of the light distribution from the ring. And then you fold that together with a model of the mass distribution of the lens. And you can actually decompose that into what looks like two colliding galaxies. Now, if you have to squint and turn your head a little bit, there's a galaxy roughly here and a galaxy roughly here, and they're interacting. Now, how can you tell that they're really interacting? This is the dust, and this is the carbon monoxide, two different transitions. And these don't actually look the same. So you can tell that the distribution is sort of roughly two different sources because the carbon monoxide distribution is not the same and at the same temperature. If it was at the same temperature, you would see roughly similar distribution of gas here and here. And so you can actually, again, map out, instead of at a 1,000 light year resolution, more like a 300 light year resolution, a source that's as far away as it is at 1 billion years after the Big Bang. So we can actually, with the resolution of this, since we can get this ring resolved so finely, and understanding from other telescopes what the mass distribution is of the thing in front of it, reconstruct what galaxies look like pretty much as soon as galaxies could possibly have formed after the Big Bang with ALMA. So where are we going next? So some other exciting things that you might expect to hear from. I expect this one to make big news in the papers, and if they don't, then they owe me a beer. So this is something that ALMA participated in last April, and it's basically an Earth-sized telescope that was that functions in the same way as ALMA. So you have the pairs of telescopes effectively talking to each other and correlating their signal. And in that way, ALMA actually acts as one single telescope. I don't do any of the correlations between them. I actually just add the signal together and ship it off to MIT. And they do the correlations of all of the different telescopes from the rest of the world. Now, what are they really trying to do here? This is a simulation of the black hole at the center of the Milky Way. And this worldwide telescope, really where ALMA serves as the anchor, because all the other telescopes are basically one 15-meter antenna or one 10-meter antenna. We have the 66 12-meter antennas that we can all add together. So we add a huge anchor down for all of these different correlations. And what they really expect to do is to actually make a picture of the event horizon. So this will be the first time that you will have actually imaged a black hole. And we will be doing it again in April this year. And I've been told that the press is sort of the material is building towards the main release, which may happen in the next sort of 2 months on order of that time scale. They haven't told me anything yet, but basically the idea here is that if the black hole event horizon appears based on the shadow from the material behind it to be circular symmetric, then certain aspects of general relativity as it stands now will be confirmed. And if it starts to look like a squished sphere in one direction or the other, then that strongly indicates that there are departures from our current understanding of how gravity works. And if they do come out with this in the sort of 2-month time scale as I'm hoping, I won't get to go, but the group of people will probably be in a small town north of here collecting a big check and a giant gold medal, probably sometime in the next year or two. All right, so the other things that we're doing is we're trying to expand the frequencies that we cover with the maximum separations of the array, and that should give us about a factor of 50% improvement in our resolution, which should really help in refining and determining the structure in the disks that the planets are forming in. The other thing we're trying to do, a little bit related to on the general relativity front, we've done this once and we hope to do it several times again soon. We're building up how rapidly we can actually observe an object if somebody tells us that something exciting has gone off somewhere in the universe. When the LIGO folks had their detection back in August last year of the gravitational wave event, we were one of the observatories that participated worldwide and following up on that. So getting to understand the nature of the environments around these sort of black hole mergers is something that we hope to participate in more going forward. All right, we also have some new windows opening up for us, and one of them is to study this guy and really determine if there is truly water everywhere, or if water is a little bit more rare than we had anticipated. So we have a new receiver on the array that's really designed to look at colder water and trying to determine where it is in location in basically planet-forming disks. So trying to figure out where the source of water in young solar systems is. And then finally, we're trying to add some capabilities to really study the full structure of some of these sort of bigger objects. Remember back at the beginning when I talked about the little blue plane that we were trying to fill up? And there's that hole in the middle that's really annoying. If you fill up that hole very well and match it, you can actually make really beautiful images of things that have very big structures and very small structures. And this is just an example of something that we have done before, but we'd like to do better. There's a young star here that has that's basically tossing a lot of material out of its poles. So it's ejecting. It has a strong jet going along these axes. And you can see this sort of basically a jet carving a hole in this giant cloud of gas and dust. So you can actually bore the hole, and you can actually determine whether or not this star, by its ejection, is actually triggering more stars to form along the edge of this. But if you want to do that, you really need to know what the bulk of the gas is doing as well as these little tiny substructures. So this is something that we hope to be doing quite a bit better in the next couple of years. But this should continue for us because the founders of ALMA were intelligent. I can't claim to have been that. I was back in grad school at that time. But they actually gave us a funding line for continued development of the observatory. So we have about 10 million euros a year for continuous upgrade to the facility. So that's how we've done things like add this special receiver. We added the capability to actually sum all of the antennas together so that we can ship them off to MIT and someone else can get famous. and also helping to support some of the studies that allow us to combine in the full signal with the combination of antenna signals as we have it. So with that, I thank you for your attention, and I'll let you get back to drinking, but please remember, if the take-home message is anything, things started much earlier than we thought, and they're much more complicated we thought, and gas and dust is really interesting.